So this is a D reason. This is a width D. So in this region, only say magnetic field is there. Outside there is 0. Here it's a 0. So only in that width region there is a magnetic field. And it's a cross. Cross means inward. Next, he say that a charged particle is shot perpendicular into the magnetic fields. So it's shot perpendicular into the magnetic fields. So he's asking to find the time spent by the particle in the magnetic fields. Okay, time spent by the particle in the magnetic field. Two cases are there: D greater than mu by bq and D less than mu by bq. Now, in this case, you can easily tell me here it's a straight line, circle, or helix. Which path it is making? Velocity is along this directions. I can take here as a x, y, z. In the x, y, z, things are easy to understand. It's a given this way. Okay? Let me consider here is a x-axis. That's my x-axis directions, and upward we can consider here as a y directions. It's not given in the questions, but we can assume x, y. So where is my magnetic fields? Magnetic field is inward. So meaning thereby it is in my z directions. Here cross represent perpendicular. It's a 2D picture, xy planes. So in this xy plane, my cross is a perpendicular. So cross represent my z directions. And that is not a positive z direction here. It's going to be inward is a negative z directions, minus k. So magnetic field is a minus k. Particle is projected here with the velocity, and that's going in my positive x directions. So where it will experience the force. If you apply right hand thumb rule, it will experience the force in the upward directions. Force will be in the upward directions. Okay? Charge is not mentioned. So when charge is not mentioned, so by default we take it here as a positive quantity. If you still have a confusions in the right hand thumb rules, you can take it here as a v cross b. You have velocity in the I directions and magnetic field in the minus k directions. So I can take here as a k cross I. So in vectors, the simple way of finding k cross I is you take the cross product of I, j, k in the circles, and the circle is going to be positive if taken clockwise. So k cross I is give me minus j. Okay, k cross I. K cross I give me plus j. In the clockwise direction, you're going here positive. So K cross I will give me here plus j. So get here plus j directions. So force is in the plus j directions. Okay. Another way is you can think of as a 3D pictures. If I think of it as a 3D pictures, this is my x, here is a y, and this one is a z. So we have a field is going to be in my negative z directions. Magnetic field in negative z directions. Charged particle is moving in my positive x directions. So where is my force? Rotate the finger from x, v to b. If you rotate the finger from v to b, so you're getting the thumb in the direction here along the y directions. Okay? Are you getting the thumb in the y direction or not? You're getting the thumb in the y directions. So here in my 2D pictures, y is up. So here is my force. Now, when it is moving in a circles, okay, just for sure it's moving in a circles. I hope so. No one have a doubt that it's a circles. How it is inside. Yesterday I told you what is the meaning of cross. Cross means inside. It's a symbolic representation of inside. Cross means inside. If you have a dot, dot means outside. Dot represent outward and cross represent inward. But here, so I hope you understand it's a circles. No doubt. It's not helix, it's not straight line, it's definitely via circles. Now for circle, what is my radius? Very simple. Radius is momentum by BQ. Now, if you compare this option, then the option they have given the D, first option they have given D greater than radius. So D here is greater than radius, meaning thereby radius is smaller than D. So it makes a semicircle, correct? But this is a D, no? This is a D here. So D means the region in which you have magnetic fields. That's my D. So if my radius is smaller, so definitely it is going to make a circle and it comes out. So after making a semicircle, it will come out. So how much time it will spend? T by 2. So first option we have already covered in the last class. So in this case, first option, your timing is T by 2. Okay, if D is greater than R, so timing here is T by 2. I hope you remember the time period formula also. Time period formula is 2 pi m by BQ. 2 pi m by BQ. So timing is T by 2. Second question here is slightly tricky. So in second question, he said that my D is smaller than radius. When a D is smaller than radius, then things is going to be happen this way. It will try to make a circles. Here it is try to make a bigger circle like this. Okay, it will try to make this way. When it try to make a bigger circles in the situations, after it will reach outside, the effect is it's going to be ineffective. Circle is going to be my ineffective. So my circle is only, magnetic forces are only effective as long as you are inside. So if you take this point as A and here is my B. So up to the B, you are part of circles. After the B, you're not the part of circles, so you go straight line. Okay, it will go as a straight lines, right? Okay, so from A to B, it's a part of circle, and circle has a center and radius. So you can think of this as a circles. Okay, AB is going to make here now arc of a circles. Like it's not looking like a arc of a circles. So let me make it here better way. Now you can see it is making an arc of circle. Now AB is the arc of my circle. Okay, AB is the arc of circles. Now in that circles, if you notice, and this just a pay here, somewhere it has centers. Now it is a tangent give me the velocity. So when it is leave, it will leave in the tangent direction also, correct? Okay, it will leave, and he asks you how much time it is spending. So time is the time taken to cover this arc, AB arc. If we know this angle here theta, I know how much time is there because I can find out the arc length in terms of theta. So for theta, we need here a little bit of trigonometry, slightly trigonometry, not complicated trigonometries. So you can take the help of this trigonometry. Let me draw here this trigonometry. You can find out the theta with the help of this trigonometry. Sevita, what is my theta? How do I find out here the theta? I know one thing, that from A to B, this is your radius, correct? I know one thing more, A to B, this is my D, because if we go from here, only this part there is a magnetic field. After the B, there is no magnetic fields. So this D is given, the radius I know. So can you find out the theta or not? It is making a right triangles. So in this right triangle, we can find out here the theta. So for the second situations, if your D is smaller than radius, so I can say that the angle subtended, okay? So this angle subtended, we can say it is given by sine theta D by R, okay? Sine theta. So timing is arc. We can find out here this timing as a arc covered AB arc divided by speed. And arc, I hope so. You can understand how to find out here this arc. I know the radius. Okay, I know the theta. So arc you can find out easily. So it will be arc theta by speed. But give me the time. So I hope you understand here the trigonometrical relation here. It's a not tough one, quite easy one. But related to this concept, there are a lot of questions. In fact, many questions you can find in the books related to these concepts. So many different questions could be designed, or they can ask you. Same question, they can ask that how much the particle has been deviated. So the angle at the centers is the same angle it will comes out. This angle is also theta. So deviation angle is nothing but theta angles. You are going along the x directions, but now you comes out theta angles. So my original direction and new directions, that is also called your deviation angles. So in same problem, they can ask you what is the deviation angles. Okay. In same problem, they can ask you distance traveled by the particle in magnetic field. So what is the distance traveled with the particle in magnetic field? Distance here is AB. In same problem, they can ask you displacement traveled by the particle. So displacement here is the vector AB, right? So many questions could be related with this concept. Or there is a lot of twisted version is there for this concept also. Okay, so it is the simplest versions in the story. So I hope you understand here. Do anyone have a doubt? Okay. Is it okay? Clear? So question is quite simple. Here is a magnetic field, and this magnetic field is not unlimited. There is a limited supply of the magnetic fields. In this limited supply, a particle enter, and it is start making a circles, but it is not able to complete the circles. So before it is able to complete the circle, magnetic field is finished. So it will comes out. So in this zone of my magnetic fields, how much part it spent, we can find out by trigonometry. And simple trigonometry is here. This is my circle radius. Okay, this width is going to be my d. Circle radius, width is here my d. So I can find out the angle it will spend in a magnetic fields. So from this angles, we can relate timing and everything else.
Sir,
Yes, Sujan.
sir, when did the class
Yes.
start, sir?
11, or sorry, 10:15. Timing today change, beta. 10:15 to 12:45. You have no idea for timing?
No, sir. No, sir. They just
No,
now I have
no
seen
information.
Just now I have seen the message.
Just now you've seen the message.
They did not inform.
I
before.
also मैं inform तो किया होगा, बाकी
Sir,
maybe.
they sent message at 10:22, sir.
नहीं, at 10:22 they just send you for reminders. I told them some of the students are missing, so they maybe send you for the reminder.
Okay.
Okay, anyway, I have not started any new topic now.
Yesterday's
know.
problem, sir.
Yesterday only problem we are discussing.
Okay, sir. Okay, sir.
So okay, so I hope that is okay, clear. So on similar concept, we have next questions. So this one, if you understand, try to give me the answer for this next question. Exactly similar concept, very similar concept. A charged particle enter in the magnetic field at right angle to the magnetic field. So already given, it is right angle. So means right angle means circle. So already given, it's a circle. The field exists only for the length equal to half the radius of the circular path. So particle get deviated. Deviations. Deviation means what? You're going in a one direction and you are comes out in another directions. So angle between the incoming and outgoing is going to be called deviations. So just like based on the last problems, you can give me the answer here quickly. Yes, Sunath.
Sir, option C.
Option C, 30 degree. Right. So very easy is there here. Because here is a circle, right? Now he say that the charged particle enter. So let's say here is my entering point. It enters somewhere. It is going to be entered at this particular point. And he say that it is not able to make a full circles. So field is only up to a half radius. So let's say the field is only up to this zone. In this zone, you have field. So there is no field outside this zone. So we have only field up to this zones. So we have this is going to be this radius, okay? Centers, radius, radius. So what is this distance? That is going to be r by 2. So this angle you can find out here. This is 30 degree. So when you comes out, you will comes out tangent. So that's my deviation angles. And this deviation and theta both are going to be same. And you can see here from the trigonometry, which is 30 degree. So we are deviating, okay, at an angle of 30 degree, right? Again, on the similar concept, you have this questions. The mostly students confuse whether it makes a circle or it makes a helix. So tell me, circle or helix? So for circle, how many of you are agree? A circle. For the helix, how many of you think it's helix? So some people are thinking it's a helix. No, it is not a helix. It is making a circle only. Why? For circle condition required is velocity should be perpendicular to the magnetic fields. So this angle theta, it's with the line PQ. This theta is not with the magnetic field. Magnetic field is with a cross. Cross means into the paper. So velocity and magnetic field both are perpendicular. No? So they are still perpendicular. So perpendicular means it is going to make a circle only. Yes? So when it is going to make a circle here, the question is, where is the center of the circles? That is the important point here in this question you have to understand. Where is the centers? So I have a velocity. This is my velocity vectors. Okay? And where is the magnetic field? Magnetic field is into. So on the right side, you have unlimited magnetic field, but on the left side, you don't have a magnetic field on the left side. Now, if I say here the direction of my force, so how I give the direction of the force. So to solve this type of problems, I told you, use right-hand thumb rules. In a tricky problem, right-hand thumb rule only going to be helpful. Other methods are not at all going to be helpful. Okay? So if you try to find out the direction of the force by other methods, it will get complicated. But with the right-hand thumb rules, only you can get here the direction of the force easily. So where is the force going? So for right-hand thumb rules, try to see. Now in this case, 3D is going to be complicate the situations, not simplify the situations. In the previous problems, your 3D simplify. But in this problem, if you think here 3D, if I try to explain you with the 3D, it get complicated. So right hand thumb rule is the best options. So what you do is you keep your fingers parallel to your, first keep the finger, which fingers? Your right hand fingers. Keep the fingers in the direction of velocity. Okay, keep the finger in the direction of velocity, and now turn your finger in the direction of magnetic fields. So where is the magnetic field? Inward. So when you are turning the fingers, it was rotating. Okay, my fingers are going to be now rotate in the inward directions. Rotate your fingers. Can you rotate the fingers? Now fingers are rotating in the inward direction. So it will give me here thumb in this way. So you're getting the thumb in your upward directions. So my force here is, this is the direction of force. That is my direction of force, and force is coming here perpendicular to the velocity. So in the direction of force, we have a somewhere centers. Okay? You got somewhere center in the direction of force. And if I consider this is my horizons, so from C to O, that gives me a radius. That's becoming here my radius. The angle is given theta. This angle is given you here theta. So I can say that it's going to make an angle here. This angle is going to be here theta also. Okay, anyway, now keeping this, it's making a circles. Okay, now you can see here circles. So with the center C, it's going to make here a circle. But it is again not a full circle. You can see here, that's not a full circles. So we have a limited circle is there. So in this part of the circles, so you are entering at some point and you are leaving at the points. So only part here is, if I consider this is my O point, so up to here, this let's say here is the O dash. So only this part is going to be a circles. So all the remaining, it's not going to be a circles. This is only going to be a circles, and then it is going to be comes out from this side. Okay, can you see that? It will comes out. So it's making a circles, and when it is moving in a circles, so at the center it is not making a full circle. It's making a part of the circles. And how much angle it is making here? 2 theta angle is the only made. Correct? I hope you understand here the directions and the center locations. How we spotted the center, that is the important thing. So how we spotted here the centers? Take that finger in the direction of velocity and rotate the finger toward the magnetic field. So if you're rotating the finger toward the magnetic field, your thumb is coming in the upward directions. If your thumb is coming here in upward directions, so in this direction of thumb, you have a force. Okay? And force must have a centers toward the centers. So just keep on bending, bending, bending. It is going to becomes out. So same question now could be asked here. How much time it is spending? So a lot of things could be asked here. First, they can ask you radius. Radius is mv by bq. Okay. Omega v by r will give me the omega bq by m. Time period, standard 2 by m by bq is the time period. If I ask you time spent, what is the time spent? Time taken to travel. So time spent here is the time to cover this arc divided by speed. And what is this arc covered? This arc covered is my radius into 2 theta. Okay. Radius here into my 2 theta. So it's a radius into my 2 theta divided by velocity. Right? Theta is given. It's given in the question here. Theta is already given in the questions. So radius you can substitute and you can get the timing. They can ask distance. Distance is velocity into time. They can also ask here displacement. Distance is not tough here. Displacement, if I can ask, that is slightly tough here. So what is my displacement? Displacement here is this vector O dash. So in this trigonometry, you can tell me here, C to O, distance is your R. So in this triangles, R sine theta. This part is R sine theta. Here is R sine theta. So can I say displacement is 2R sine theta? Okay. So I can displacement here is 2R sine theta. Put the value of R. They can ask you what are the coordinates of the point from where particle leaves. So you can find out the O dash coordinate also. They can ask you what is the coordinate of the center coordinate. You can tell me the center coordinate also. Okay. What is my center coordinate here? In my x directions, center coordinate in this triangle is r cos theta. In my y direction, r sin theta. So center coordinate is r cos theta. Y direction here is r sin theta. Center coordinate. They can also ask you deviations. Deviation is incoming direction, outgoing directions. So that is called here deviations. Incoming direction and outgoing direction. That's called deviations. So this angle here is my deviations. Just by simple trigonometry, you can give me here the deviations. It's a velocity and it will turn by 2 theta. So if my radius turned by 2 theta, then velocity also turned by 2 theta. So I can clearly say my deviation angle is same as radius rotated. So deviation angle here is twice theta. So many ways these questions could be asked, but all the questions approach in the similar way. And in that, directions play the most important roles. Okay with that? I hope you understand. So anyone have a doubt in the directions? Yes, I.
Hello, sir.
Yes, I. Tell me.
Sir, can you scroll up, sir, above some?
In this problem, any doubt is there or not?
No, sir. No, sir.
Anyone else have a doubt in this problem? So this is one of the very foundation problems. Okay, so many questions are linked with these problems. So it should be very thoroughly clear. So I hope, is it okay, clear?
Yes, sir.
Anyone have a doubt in the problems? So if you understand these problems, you can understand this chapter also easily.
Sir, one time
So
can you
next-
scroll up, sir? Yes, sir.
Here,
Yes. Thank you, sir.
so all the problem I have discussed, they are linked. Okay. Next question, it is the same one. Okay, it's the same one. It is in the next question, it should be a negative charge. You try with the negative charge. Okay. Same question as upper one, just try with the negative charge. So I hope you understand the circles. So if you understand here the circle or force experienced by the charged particles. Now we can go to this next concept in the chapters. That is a force experienced by the current carrying wire. Yes, Satish.
Good morning, sir.
Good morning.
Sir, now only you started the concept stuff.
But we started the class at 10:15 and
sir,
we
not-
just
I mean,
discussed the
You
problem.
have started only concept 9 right now.
I'm going to start the concept now.
Okay, sir. Before that, you had taught only questions, sir.
Yesterday question, we have discussed the questions on the yesterday topic.
Okay, sir. Thank
ठीक है बेटा?
you, sir. Yes, sir.
Yes, Prem Garu. Love boy. Hello.
What up to?
What?
Class up to, sir.
I'm not getting your voice clearly. What are you asking?
Class ends at what time, sir?
Today timing is changed. It is 10:15 to 12:45.
Daily,
But don't worry.
daily
I
same
think
time,
so.
sir.
Daily it will be 10:15. So I don't know how you are not getting the informations. It happens. Okay, let's start here. Our new idea here is ampere force. In this ampere force, the lot of things are similar to your last topics. Approach is almost similar to the last topic, and in this topic also, direction is the dominating one. Okay, direction has to be understood here clearly. So in the books, you don't find the name ampere force. Okay, in the books here they are saying magnetic force on a current wire. That is the topic name. But it is not a magnetic force. It's a totally new types of the forces there. That's called ampere force. It looks like a magnetic force, but it is slightly different from the magnetic force. So you will understand the reasons why it is look like and why it is different. So basic concept here in the ampere force is it is the force experienced by the current in the magnetic fields. If you have magnetic fields, okay, magnetic field is there. The magnetic field can be created by the magnet. Let's say here is a magnetic field, and when charge is moving, it will experience the force, and here is a current. Current is also made up of charges. Okay, so this current will also experience the magnetic force, and the force experienced by this small part, not total wire. Remember, here it's a very small section we have considered. So force experienced by the very small section is I dl cross B. Okay, I dl cross B. This ideal current into the small elements, small length, that's called current elements. So you can say force is a current element cross magnetic fields. Right? So this force experienced by the small element is I dl cross B. So direction again given by your right hand thumb rules. So in this case, you have to take the direction from current to magnetic fields. So suppose that here, let me consider this one situation. The current is going to be flow in my x directions. Okay, current is flow in my x direction, and we have a magnetic field in the z directions. So in which direction it will experience the force? So it's given by right hand thumb rules. So you take that finger in the direction of my current, and then you rotate the fingers in the direction of your z. So if you take the fingers and then rotate, okay, so we are going to be rotate in the direction of my z. So your fingers is going to become like this. When it is going to rotate this way, okay, fingers are going to rotate this way. Your thumb is going to be coming in this directions. So it's coming out to basically a y directions. Okay, you rotate the fingers from current toward the magnetic fields. If I rotate the finger from current toward the magnetic field, it's coming in my y direction. So force will be in my y directions. So exactly same right hand thumb rules. So let me twist the situation slightly. So a lot of easy problems direction we have given. I slightly going to be here twist it. Direction wise, just direction wise I'm twisting here. Okay? Question we are not twisting here. So let's say my current is, this is the direction of my current, x, y, z is the direction of my current. And we have a magnetic field is, that is the direction of my magnetic field. The magnetic field is making an angle of 30 degree with the y-axis and 60 degree with your z-axis. So in which direction it will experience the force? In which direction it will experience the force? It is a simple one, but angle creates illusions. Angle here is creating here the confusions. So in which direction it will experience the force? So anyone want to give the answer here? Current in the z directions, magnetic field makes an angle 60 degree with the z-axis, 30 degree with the y-axis. So what is the direction of a force? Yes, Akash.
Sir, when did the class start? I joined just now, sir.
Actually, today timing is 10:15. Okay, but topic I just started. Topic I have not
Okay,
started.
sir.
Okay. Oh yes, Arvind Garu.
Sir, negative x-axis, sir.
Negative x-axis, correct. So direction of force is negative x-axis. Now here, if you think in your 3D way, so 3D way is going to create a confusions. Okay. 3D way here is going to confuse here the confusions. That's why we have taken the cross concept. If you analyze, what is this force? Force is perpendicular to the plane of L and B. L direction is my I direction basically. Okay? So it's a plane of my I and B, current and magnetic field planes. So if you notice my current and magnetic field planes, current in the Z directions, magnetic field in the Z and Y planes. So I can consider here planes. So in this plane, I have a current in the direction of my Z axis, or current element, you can say Z axis, and I'm going to have a B. B is going to be in this planes. So magnetic field lies in the YZ planes. So where is my x-axis? So if you think of x-axis, so x-axis is going to be in your outward directions. It will appear as a dot. X-axis is going to be a dot. Okay, it appears as a dot. It is out of the papers. If you think of 2D. Now, if you try to now rotate your fingers, so if your fingers should be in the direction of your fingers should be in the directions, and you have to rotate your fingers from Z to, you have to rotate the finger from Z to Y, current to magnetic fields. If you rotate the finger from current to the magnetic fields, your thumb is going in the inward directions. So your x-axis is outward and your thumb is going in the inward directions. If thumb is going in my inward directions, so my magnetic field, force, this force is negative x-axis. So direction of the force, I can say here it is in my minus I directions. Okay? Minus I directions. So I hope you understand here. So 2D is also play a very important role. Sometimes 3D explain the direction easily. Sometimes 2D explain the direction easily. Okay. So both direction, both method is important. We should analyze in 2 dimensions way and 3 dimensions way. But important here is the clarity. So anyone have a doubt in the direction here? Y minus X? Oh, yes, Sunat. Hello, Sunad, I'm not getting your voice.
Sir, you can hear me, sir.
Now I can hear you. There was a direction. In this 3D picture, y-axis, z-axis. So in this 3D picture, I have given you current along the Z, and the B is making an angle 30. And this magnetic field vector is lies in your YZ planes. And force is a cross product of your current and B. Means it is perpendicular to this plane. And how we give the direction is cross product, dl cross b. So you have to take the cross product of this dl cross b, ideal cross b. So if you take a cross product, so cross product is perpendicular to this yz plane. Okay? So perpendicular to the yz, you have x-axis. But where is my x-axis? If you think from this yz, my x is outward. So x is a dot. Okay? X here is a dot. And the cross product, to get here the cross product, you have to rotate the finger from Z toward the B, current to magnetic fields. So what you do is, you take a fingers, your finger should be parallel to your Z axis. Okay? Finger should be parallel to your Z axis. And then you rotate your finger toward the B, magnetic fields. If you rotate your finger toward the B, your thumb will go inward. Okay, it will go here in the inward directions.
Yes, sir.
Here you are going to be turns, and I can say here this rotation is theirs. You're getting here thumb in the inward direction. So force will come in the inward directions. Right? So I hope you understand here and directions. Why that force is coming. So we can understand this force with a simple proof is there. So very simple is, because current is made up of moving charges. Electrons move and they generate here the current. Okay, so current has a velocity also. Charges moving, so they have velocity, drift velocities, remember? And what is the current and drift velocity relation we had derived in this last chapter? So it's a NeVDA. The current is depending upon my NeVDA. Here VD is a drift velocity. So my current depends upon the drift velocity. If I just take a single electrons, one electrons. So on the one electrons, the force is Q V cross B. That's my force on the one electron. Q V cross B. Q is negative, it's minus E. And velocity here is a drift velocity. So that is the force experienced by the electron. So if we multiply the number of electron with the force experienced by the one electron, I will get the total force experienced by the one. So in that small section, how many electrons are there? The small section, if you consider a small length, if you consider dl, so it is like a volume. And small n, if you remember, small n is a number per unit volumes. It's a number density. Small n we have taken unique for every metal. So every metal has a unique concentration of the electrons. So total number in the volume, in the small volume, is the area into length into my density. So that's our simple, okay, numbers. So for one electrons, that is the force, multiply with the number of electrons, that will give me the force experienced by all the electrons, right? We can say that. So idea here is you just multiply the number with the force. So number here is NA dl, and force on the electron is QVB, QV cross B. So here dl, remember that dl is a very small quantity. what is the DL we had taken? DL we had taken that length of my wires, small sections. So this DL directions and that drift velocity directions, they are basically same. So we can take the DL inside the vector and the direction VD you can take out of the cross product. So DL we can take here inside the cross product and VD we can take out of the cross product. So I can get here this relations. Okay. Now this NEAVD that represent my currents. So I can got the force as a IDL cross P, right? Okay. IDL cross P, that is the force experienced by the small sections. Yes, Sunad.
Sir, can you explain the direction of force in the first diagram, sir?
Direction of force where?
First diagram, below the.
This diagram.
No, sir, above the.
ये वाला?
Sir, above, sir. First one.
This one. This one.
Ah, yes.
क्या ये direction नहीं है इसमें? That is just roughly I have given. This is not going to the directions.
Yes, sir, I was getting
ठीक है?
different.
No, not this one. This is not correct directions. Okay, what I am explaining here is that, so this small sections, if you consider here the very small sections, and this is under the magnetic field, it will experience the force. So force is coming because of my current. Current is coming because of the charge velocity. So if we know the force on the 1 electrons, we can multiply with the number of electrons, and I'm getting the force. Now here, you can say that it is a magnetic force. Why a new name is given? In the books also, you will see it's named as a magnetic force, but it is not a magnetic force. So where is a twist? Twist is going to be lie here in this equations. Here in the equation, we have taken drift velocity, and drift velocity is caused by collision also. Drift velocity is not the velocity of the electrons. It is the average velocity of the electrons. Or in that average velocity, collision also come into the pictures. Okay, so there is a pushing electric field is also there. So in this drift velocity, electric field collision effect is there. Okay, so here, if I say it is a magnetic force, so it is not a alone magnetic force. It includes the collision and electric force effect also. So the result come from that is not purely magnetic. That's why it is wrong to call it as a magnetic force. But in the books, it is written as a magnetic force. So I'm also using the same name as magnetic force, but actually it is not a magnetic force. I hope you understand the point, yes? So that's why it's not a magnetic force. So all the confusion regarding the magnetic force comes from the same equations. So remember here, VD is the effect of electric and collision forces. So because my force on the electrons depends upon the VD depends upon the electric field and collision forces. So I can say the force on the electron is not purely magnetic. Okay? So it is not purely magnetic. So it's going to be called a new name that's called Ampere force. Okay. In depth, how it is created, mostly we not require it. Okay, so you need not to be bothered much in the directions. So I don't expect that to be go in that depth. So you can think of it as a magnetic force. So there are lots of interesting features of this force. The first important thing is current is something which is same everywhere. In a wires, your current is same. So every element have a same current. So I can take out the current outside. Now it is an integration over the DL cross P. As a very special case, it's a special case, okay? Not a general. So as a special case, if B is a constant, so B is also out of the integrations. And if B is also out of the integration, what is left in the integration? Only DL left in the integrations. If DL left in the integrations, so I can say that force, total force is I L cross P. So here L means what? It is a vector sum of all the elements. So suppose here we have a wires from P to Q. So L is a vector sum. So it is basically going to be my vector PQ. Okay. So for constant magnetic fields, in many problems you have a constant magnetic field. So it is a easy way. But I suggest that it is most of the situation you have a constant magnetic field. So you can call this is a force. So in this force, L becomes the length. Okay, L vectors. So which length you have to consider? Not the wire length. L here is not the wire length. It is the length from the starting to the end point. So it is the length from P to Q. Or in simple language, you can call this force as a Bill sine theta. So it is going to be used in many problems. So students think that this is the force. It is a special case of the force. So Bill sine theta is a special case if B is a constant. If B is not a constant, then B is also inside the integrations. Then you're going to apply that Bill sine theta on the small element and then integrate. Okay, so we have here advantage. What is the advantage? The advantage, big advantage is that if you have a long wires, so in the long wire, it doesn't matter where the wire going. Only matter is from where the wire starts and where the wire end. So P and Q length is only going to be matter. So suppose here I have a current enter at the A and current leave at the B. Okay, entering at the A and leave at the B. And I have a magnetic field in the direction of your diagonal AB. That's my directions. So you can consider the radius is something as R. So what is the magnetic force experienced by this total wire? Magnetic force experienced by the total wires. The formula is for the small part. Okay. Formula here is for the small part. But because it's a constant magnetic field, so I can forget about the small part and we can only focus on the endpoints. So I can replace this whole structures as a single wire AB. So force experienced by the single wire AB is the same as the force experienced by this curved wire AB. How can we replace it? We can replace it if B is a constant. If B is constant, you can replace it. If B is not constant, then you can't do it. So under my constant magnetic field, I can replace the curve with the straight wires. Now for this straight wires, it is a length of diameters. And here's my force is Bill sine theta. So I can say my force is equals to I L cross B. If I open it, it will be a B I L sine theta. Okay, Bill sine theta. So in the sine theta, what is the angle between the L and B? L is my AB vector and magnetic fields is also there. So angle basically 0 degree. So an angle here is 0 degree. So I can say the force is also going to be 0. So even though wire is curved, but its end are in the direction of my magnetic fields. Ends are in the direction of magnetic fields. So in this cross product, angle goes to be 0 and your force goes to be 0. Okay. So most of the times, this approach is very useful. So you can replace the curved wire with the straight lines. Yes or not?
Sir, what does negative sign represent? Sir?
Negative sign where?
Sir, we took force as restoring. So why did we take that as restoring force?
So restoring नहीं है वो. That's not a restoring. It is not important. That's not restoring.
Sir, we took force on each particle as minus EABD.
Repeat again. We have taken
Force on each particle as minus E into VDB.
yes, we have taken here. Actually, the direction of current is opposite to the direction of your negative charges. So this negative sign will be included into the velocity. Here we have the current is equals to NEA VD. So in this this negative sign is theirs. Okay. So if it is negative sign, current is also going to be written here as a minus NEA VD. So this negative sign is covered in the current. So in the formula, there is no negative sign. It was IDL cross P. Okay. So the important here is that if you have a uniform magnetic field, I can replace the curved wire with the straight wires. Very good. Suppose next here is if you can replace. Okay. In this case, because in this luckily force was 0. But if force is coming, so where should I take that force point, application point of the force? Where should we apply the force? Because if the force experienced by the curved wire, so at what part of the body you are going to be applied? So in this case, you are going to be applied on the midpoint. Okay? The force is applied at the midpoint of the wires. To get a little more clarity, if you see this, some more questions, okay? It get easy. So suppose here a triangle is given, and in this triangles we have a current flow. 5 ampere current is going to be flow in the triangle. Sides of the triangles are given, and magnetic field is given as a cross. So I hope you can see crosses into the paper. So he's asking here, find the force on the 3 sides of the triangles. It's very easy. Find the force on 3 sides of the triangles. Zero or non-zero? See, Rita, if you have a closed structure, current is going to be making a closed structure. So force here is I dl cross B, and B here is constant, so it will out of the integrations. So what is the vector sum of all the dl? If I take out small dl, so small dl, if you add up, so all that small dl you can add up. So what is the vector sum of all the small dl? So for closed body, it is 0, no? Always. So for this closed body, this always comes out to be 0. So you can start from the A, you can return back to the A. Okay. So on this closed structures, DL term is 0 if B is out of the integrations. So for any closed body, you can say force is 0. Okay. So this is for any closed current loop. Any closed current loop. So in this question, they have given triangles as a closed loop, but they can give any complex structure also. So in a complex structure also, you can get the same result. चलो ये तो हो गया. अच्छा, one more question I can give you here, twisted ones. This part we have already covered. So imagine we have a cube. And current is enter at the one end of the cube and leave at the another end of the cube. Okay, so how is the current coming? So current is entering at the one end and it is leaving at the another end. So let's say it is going to be entering at my this end A, and it is leaving here diagonally to my this end. Current enter is a I, current leave is a I. Each side of the cube is a. Okay, each side of the cube is A, and we have a magnetic fields in the direction. In this direction, we have magnetic fields. The question is that find the force on the cube. What is the force on the cube? Yes, Akash.
Sir, √3 BIA.
√3 BIA.
BIA.
Okay. Answer. So देख लेते हैं. Let's see. I don't think so. It is a √3 term will come. Answer I don't know, but it seems to be a little wrong. So anyone else? So current go, okay? Current go many way, but what is the beauty here is you can replace that cube with the straight line. So you can replace the cube with that straight line here AB. Okay? So you can think of cube here as a AB vectors. So if I think the cube as a AB vectors, it's my magnetic field is along this side. If I take it here, this side is something X. So magnetic field is along the X-axis. And current, you can just replace whole of the cube with the simple AB line. Okay? Simple AB line. Now in that AB line, if we try to draw, I can think of this way. So there is a magnetic field. Okay? Magnetic field is there. And I can replace my current wires with the AB lines. So this is my AB lines. It is going to carry the current. Now what is the angle between my AB line? Length is √3a. Current is I. But how much is the angle between the line AB, diagonal AB, with that magnetic fields? Okay, magnetic field is along one of the sides. Can you see that? Magnetic field is along the one of the sides. So you have to tell me the angle made by the diagonal with the side. So for that, we can take the help of a little bit of trigonometry. So here is my diagonal AB. So I want to find out the angle made by the diagonals with the side AC. So this could be done with the trigonometry. So if you see in a triangle ACB, so I want that angle here theta, the angle between the AB line and AC line. So that's it. So in a triangles, if you just focus in the triangles, so in a triangle AC is a, and what is my BC? Okay, forget about the BC. What is my AB? AB is a √3a. And it's a right triangle. ACB is a right triangles, correct? In a triangles ABC, angle C is a 90 degrees. When angle C is a 90 degree, I can use here my cos theta. So cos theta is nothing but it's a AC by AB. I hope this trigonometry is okay, clear? Angle C is a 90 degree. It is not looking 90 degree, but think logically. AC is a side and BC is a diagonal. Okay? And this face, BC face, is perpendicular to the side. So this AC is perpendicular to my BC. So in this triangles, right triangles, I can say in my theta, cos theta is base by hypotenuse. So base by hypotenuse. So getting here 1 by root 3 is a cos theta. So it's a whole of the cube we can replace with the AB line. So there is a current AB, there is a magnetic field, and there is an angle between the magnetic field and the current. And this angle is my theta. Now I can apply for the force. Okay. This question we already discussed here. So force here is IL cross B. So I can say BIL sine theta, Bill sine theta. So cos theta, I know 1 by root 3. So sine theta, you can tell me the value of sine theta. Okay. Cos theta is 1 by root 3. Sine theta will be equals. If we take it here as a, just a minute. Cos theta is 1 by, cos theta is 1 by root 3. So perpendicular will be root 2. So sine theta will be root 2 by 3. So with that trigonometry, now we can say what is the force. Current is I. Length is my root 3a. Whose length? Whole of the cube I can replace with. So in whole of the cube, we can replace the sine AB. So this AB is a diagonal, body diagonal. So it's a root 3a. Magnetic field is a B. And angle between. So that gives me the force. So I hope you can understand that this approach of replacing the curved body with the straight lines, it's a very powerful approach. So a lot of complicated problems could be easily solved. But when you can apply this approach, it is applicable when B is constant. And okay, so it is applicable to the maximum problems. I hope you understand this approach. Wherever you have a constant magnetic field, don't bother about the shape. Forget about the shape. Simply take the starting and ending point of the current. Okay, rest is trigonometry. So anyone have a doubt in this approach? Very good. If you understand the approach, give me the answer. I will not give the answer here. So next question, you give me the answer here. Current is moving like a snake in a sine functions. So he's asking the force. And you also tell me the direction. And the question is force also. Now here, just by seeing that the functions, so many students get confused and they feel that something complicated is coming. No, you need not bother about the shape. What is bother? Only starting and ending. Okay, just bother about the starting and ending. So you can replace that sign with the single current. So you can consider here as a single current is, oh, sorry, you tell me the answer. Yes or not?
Hello.
Yes,
Sir,
Punarbhita?
0, sir.
0. No, 0 is not the answer. Arvind.
2IBL
2IBL. IBL.
along y-axis.
Force direction is along y-axis, correct. Force along y-axis direction and 2IBL. C answer.
Sir,
So what you have to do?
one force is
yes.
along positive y-axis and another is negative.
No. Stations. You just replace with the end. You just replace this whole of the current will be replaced by this rod. Okay. Right here in the integrations, it's going to be so opposite where also it was so opposite, but we have replaced with the ends only. So you can replace the whole structure with the end. So just replace the whole structure with the end. Okay.
So direction of current we can direct.
First thing is that is the effect of the curve. The effect of the curve is not important. Force is given by these integrations. So what is left in the integration is my DL. So what is this DL? This DL is the small elements. So if you vector sum, so what is that vector sum give me? This vector sum give me here from starting to ending. Just take a length from starting to ending. That will give me here this total vectors. If I call this length as a AB, so I can replace this total wire with the AB length. So forget about the shape, replace by a straight wires. So if you replace by the straight wires, so I'm getting here the force as a I L cross B. Here L is going to be the length from starting to ending. This is my my 2L direction. So L vector is basically 2L and direction here is a minus I cap. Magnetic field is a B, and its direction is minus K cap. So you're getting the force 2ILB. Okay, I cross K. And what is I cross K? It's a J. So force will be in your J directions. Force you can also find out by the right hand thumb rules. If you rotate the fingers from X directions inward, magnetic field here is inward. Current in my X direction, magnetic field here is inward. You rotate the finger, your finger will go down, thumb will come in the, okay, from the right hand thumb rule, you're getting the direction of force along the Y direction only. So is it okay? Clear? Shape not matter if magnetic field is constant. Right, Rita? Problem. And this force could be used anywhere. Now this force has have a same effect as a tension, normal, friction. It could be applied anywhere in the mechanics. So you can use this force anywhere in the mechanics, and questions could be twisted in many ways. So one simple questions without twist, we can consider here with the effect of mechanics into adding into our ampere force. So here we say a straight mass given, length given, current given, and it is suspended in the mid-air by a uniform horizontal magnetic fields. So how much magnetic field is required? Okay. So it is suspending the wire the weight magnetic force. So he's asking the value of required. It is possible. Again, it is possible here. If I consider directions, if my magnetic force is exactly opposite, it is possible. It is possible to cancel out. And this magnetic force can be created if there is current, it has some length is there, and you can put some perpendicular magnetic fields. Because parallel magnetic field does not give any force. Only perpendicular magnetic field gives a force. It's a dl L cross P. Perpendicular contribute. So if I take a magnetic field perpendicular to the current, it can suspend it. So let's say here, this is my, here is my another axis, and here is my vertical. So for force, to get the force in the upward direction, where should I put the magnetic fields? We have current in the x directions. Okay, here is my current, let's say it's a y, this one is a z. So where should I put the magnetic field? So magnetic field must have a perpendicular components. Okay, and this magnetic field must be have a perpendicular component to the current. It must be perpendicular to your force also. So my magnetic field should be in the y directions. Now in y, two possibilities are there, plus y or minus y. So which direction should I consider the magnetic field? Plus y or minus y? So you can give it here by right hand thumb rules. I want my thumb to be in the upward directions. Or if you rotate your fingers, so your thumb in the upward directions, finger in the direction of my, here is my thumb is going to be in my upward directions. And my finger going to rotate. So my finger is going to be rotate, right hand finger. So it will be rotate toward the y directions only, correct? The force must, so field must be in the y directions. Okay. Okay, question is not asking the field directions, but you should know the direction always. This chapter is mainly about the directions. Yes, Durga Prasad.
Sir, answer is 0.65 only, sir.
Check it. Let's check it here. So I can have a field and the force is equals to your BIL, sine angle here is a 90 degree, force you can say as a mg, this is going to be mg, current, and you can find out the value of B. Okay. So there is a one twist is there in the question. It was not in the question, but in the concept there is a twist. So theta is not necessary to be 90 degree. You can have a theta non-90 also. We required some force. So magnetic field should not be parallel to the current. Okay, but it is not necessary that magnetic field is completely perpendicular to the current. If my magnetic field is parallel to the current, force is 0. Okay, so one component should be there, perpendicular component should be there, completely magnetic field should not be perpendicular. So I can say here, theta is not necessary to be 90 degree. If I take here theta to be 90 degree, this will give me the minimum possible value of the field. So in the questions, he should ask about the minimum. So there is a little correction is there in the questions. So it should be about the minimum. So for minimum, I can say theta should be 90 degree. Okay, because when sine theta maximum, then your B is minimum. So beta minimum is mg by IL. I hope you understand that idea. So that was a little bit of a problem with the questions. He's asking magnetic field, but you can't find out the magnetic field. A lot of possibilities are there. So magnetic field could be in this direction. Okay, magnetic field could be, the direction is not, he's asking here. So I need a magnetic field perpendicular to the current. Component of the magnetic field is required perpendicular to the current, but total magnetic field perpendicular to the current is not required. That is only required for minimum case. I hope, is it okay? Clear? No confusion? Is that okay? Clear? So there are many ways they can add up the mechanics. So they can put a spring also. I can suspend here with a spring. So there is a spring, current is passing, so spring get compressed. Okay, so like that. Same question could be asked in a many different way. Sorry. So next question here is again adding the mechanics. Slightly it's tricky. So try to think over it. So he say that conducting rod mass length, it is placed in the east-west direction on a frictionless horizontal table. And horizontal component of the Earth magnetic field is from south to north. If a charge is suddenly passed through the conductors, then instantaneous velocity acquired by the rod is instantaneous velocity acquired by the rod. So here, just try to your rod is yours. Okay, current is coming and current here is going. Current I enter, current I here is going. So next he is asking is velocity. So for velocity, how can you get here the velocity from the current? No? Current give me a force. Current gives us force. But a force can give momentum or not? Force can give momentum, right? Our velocity. So suppose that we have a force is coming because of the current. And you can do the integration over the times. If you do here the integration over the times, L and B, they're not changing with the time, so that will be out of the integrations. So integration is on the current only. So this terms gives me impulse, magnetic impulse. That's getting here the impulse. An impulse can change your velocity. It can change your velocity. So this side, you can say here my impulse, magnetic impulse, we can call impulse as a Q L cross P. So magnetic force or ampere force is I L cross B. If I'm going to be flow the current in a very short time intervals, it can give an impulse. So every force can give momentum change. It can give here the velocity change also. So same as here. That's my impulse. Okay. Sometimes it is called here as a magnetic impulse. So it is also written the same way, QL cross B. So now you can think about this question here. So in the question he say that there is a current flow in the east-west directions. So first we draw here the directions. Where is the current flowing? Current is going to flow in the east-west directions. And this one be down. So magnetic field, earth magnetic field, he say horizontal component earth magnetic field from south to north. So that is my field directions. So like which south to north. That's my B. What about the current? Current is going to be passed from east to west directions. East to west directions. So we have a rod is there. So here is my rod and current is going to be passing, entering the rod and it is going to be passing this way. So good. Now if my impulse is coming, so this impulse direction is L cross P. So L here is my starting point or ending point. So AB directions. So you can take here that impulse. It will get the impulse. Impulse is going to be suddenly, just like suddenly if you hit the ball with the, bat, it will suddenly change. It will gain the velocity in a short time intervals. So same way here, this current is passing here very shortly. So when the current is going to passing here very shortly, it will give the impulse. And the impulse is L cross B. So if I write this value, angle here is 90 degree. Magnetic field we have in the direction of north, and the current is going in the west direction, angle is 90 degree. Sorry, that's my impulse. Now he's asking velocity acquired by the rod. So first tell me the direction of velocity. It will go up or it will go down. Will it jump up or it will jump down? So direction is I cross B. Direction here is I cross B. If you rotate the thumb in the downward directions, so velocity should be in the downward directions. Okay, it will be in the downward directions. So here in the questions, he's not asking the directions, but in case suppose that in the question he say that it is placed on the ground, so it can't jump, because if it is placed on the ground, it can't jump down. Direction. I cross B. Rotate the fingers. Take the finger in the direction of your eye, and now rotate the fingers toward the B. And your hand. Your left hand will be easily rotated from I to B, but for your right hand, you have to twist your. Can you see that? Can you do it? So it will. It's going to be a twist. So you have to first rotate your hand. Okay, twist your hand, and then it will rotate from I to C. This diagram is giving a wrong impression. So you have to rotate the fingers from I to B. So another way is you can think of this way also. We can use our ijk also. Current in this direction of my west. Okay, if I take this as a x direction, this as my y direction, this as my z directions. So I have current is my j directions and magnetic field in my I directions. So impulse will be in the j cross and j cross I, it will give me a k or minus k. It gives minus k. So it is going to be a minus k. So getting the velocity in your minus k directions. Okay, can you see the directions? Does anyone have a doubt in the directions? Show your hand in the video directions. Not understanding. So you do one thing. Take your finger in the direction of current. Okay? Take your finger in the direction of current. So if you take your finger in the direction of current and try to rotate toward the magnetic fields. So your left hand easily can rotate. Okay? If you try to rotate your left hand, it could easily rotate. If your left hand can easily rotate, left hand is giving me a thumb in the upward direction. So it is going to give, right hand will give me opposite directions, downward. Or second way is you can use this ijk, take the help of your ijk. We can take the help of ijk. So my current is in the direction of your j and your magnetic field in the direction of your x. So what is the direction of my j? Current in my direction of j, magnetic field in the direction of my I. So rotate. If we take here this help of j cross I, so j cross I, for positive it should be clockwise. So if you take here j cross I, so j cross I give me here negative k. If I take I cross j give me plus k. J cross I, it gives minus k. So you can also understand the direction this way also. Okay, minus k directions. So downward directions. Right? So, okay, so I think velocity you can now find out here. Impulse is changing your momentum. So what is my velocity? So change of momentum is equals to my impulse. Initially you are at rest, then you suddenly get here the velocity. So that gives me a velocities. Okay? So many way IIT can add up the mechanical effect with the okay, good. So next question here, it's also very important one. And there is a many variation is there for these questions. Okay, many varieties are there. The most important thing is understanding these diagrams. So if you read the question, he say that there is a two long rails, metal train. If you remember trains. So these are the rails of a train. Okay. Gives the practice on the RC circuit. Regarding the RC circuit, for RC circuit, potentiometer wire, voltmeter, ammeter, RC circuit. Together, we got the 3 days in the schedule. Okay, including potentiometer, voltmeter, ammeter, meter bridge, post office box, and RC circuit. We had the 3 days in the schedules. We have spent more time than given in the schedules. And this is also important topic. So to understand the RC circuit, we have discussed many problems. So if you getting a problem in the RC circuit, so you need a practice on the circuit. Not RC circuit. So if you got the time, I will discuss definitely. Okay. But this week it's very tough to get the time. So let's see here quickly. So what is given here in the situations? Okay. So they have given rails. So it is going to be a train. Train is going to be run on these rails, right? So these rods, it's a metallic trains. Remember, trains are metallic. Rails of the trains are metallic. So he say that these 2 long metal rails are placed horizontally and parallel to each other at a separation of L. So this separation is given something as L. A uniform magnetic field exists in the vertically downward directions. So this cross, what is the meaning of the cross? Here, cross representing magnetic field. A wire of mass M can slide on the rail. So this is your wire. I can make it here as like a rod, current source. Here it is connected to a source, battery, something like that. And what is the criteria is that current through the source, the friction coefficient between the rail and the wire is mu. Okay, where is the frictions? Here is a rod. Below the rod, there is a rail, and it is touching the rails. If you think from the side view, let me make here a side view. So in the side view, this is my rail from the side view. And the rod is going to be look like a block or balls. Okay, rod you can think of as a block. So that's my rail from the side view, and this is going to be a rod from the side view. So current is passing. So we have a current, let's say I current is there. A magnetic field is downwards, vertically downwards. So magnetic field is downwards, so from the side view. So current is there in the rod, and now from the side view, current is cross. Magnetic field is vector. From the top view, this is top view of the pictures. You are watching the train from the top. So magnetic field is across. Okay, and current is going to be flow as a vectors. So I hope you can see that if you take it from the side view. So side view you can take from the left side or right side, doesn't matter. So direction. Okay, anyway. So next, see, given the mu, there is a mu surface is there. So that surface we have, mu is given between the rod and the rails. So question is that what is the minimum value of the mu which can prevent the wire from sliding on the rails? Okay, you don't want the rod to be slide. So question is quite simple, only if you have a clarity about the diagrams. So anyone have a doubt in the diagrams, situations? So now tell me the direction of force. I cross B. I inward, current is inward. Magnetic field here is downward. So what is the direction of my force? I cross B. If I try to take it here, this is a B and current is here is my inverse. So I cross B, where my I cross B is going? It will be go on the left side. So I cross B, the magnetic force will be on the left side. And this magnetic force is perpendicular to both current and B. So my magnetic force is perpendicular to magnetic fields. So magnetic field is vertical. So magnetic force will be in this plane, perpendicular to vertical, it will be in the plane. And magnetic force is also perpendicular to the current. So it is perpendicular to the rod also. So you're getting a magnetic force perpendicular to the vertical directions because B is vertical, so force is perpendicular to my B. So magnetic force is perpendicular to current also. So it is perpendicular to rod also. So you can see there is a magnetic force is coming. Now the magnetic force try to pull the rod on the left side. So friction come at the contact point. Okay? So friction is going to be coming in the back direction. Criteria is that this friction is yes, this magnetic force smaller than my mu n. As long as magnetic force is smaller than mu n, it is going to remain at rest. No sliding. The magnetic force we can see here, it's the BIL sine theta. Theta here is 90 degree. Which angle is 90 degree here? The angle between the current and the magnetic fields. You can see these pictures. So current is in the plane of paper. Magnetic field is perpendicular to the plane of paper. Magnetic field vertical, current in the horizontal rod. So perpendicular 90 degree. If you think from the side picture also, so we have magnetic field vertical and current. Okay? Current is inward. It should be less than our mu n, and here is my mg. So you can get the condition on the mu. So mu should be greater than our BIL mg. Right? Not a tough questions. But of course, if you are not getting the directions or diagram clearly, it could be confusing. Yes, Akash.
Please explain the direction once again.
Direction, okay. So direction we can once again. What is the picture given to you? This picture is from the top. It's a top view. Okay. So if top view is given, so sometimes side view is very helpful. So in this top view, magnetic field is inward into the paper. Current is coming here downward. Okay. Current flow like this. So I can say my force direction is I cross B. I downward, magnetic field is inwards. So if you rotate, it will comes out to be in the other side. In this picture, your force will be on the other side. It will come on the other side. So current is downward, magnetic field is inward. So I cross B. But this force is perpendicular to my magnetic field, first thing. The magnetic field is into, so force must be in the plane. And this force must be perpendicular to current also, because it's a cross product. No? So cross product is perpendicular to both the vectors. So it should be perpendicular to the current and perpendicular to the fields. So it will be on the either left side or so left or right, it will be decided by your thumb rules. Right hand thumb rule you can apply. So for this given directions, here in the direction given in the pictures, if I take a fingers in the direction of your current, okay? and rotate your fingers in downward directions. First, you make your fingers straight in the direction of current and then rotate toward the magnetic fields. ठीक है? So it's a need to be slightly twist your hand. You have to be twist a little bit of your hand. Or if you have we can see from the side view pictures. If we take it here side views, in the side view, I can take from this side or I can make a picture from this side. So let me pick the picture from this side. Okay, last time I make the picture from this side. Let's say we draw the picture from this side view. Okay, you're watching here from this side. You're watching from this side. So rail is theirs. That's my. And in which direction your current is coming? We are watching from this side. So current is coming out, so outside. So it will appear as the out of the plate. Okay. So person is watching, so it will be toward the person. So it will appear as a dot. The current appear as a dot. We have magnetic field in the vertically downward directions. So magnetic field here downward, current as a dot, and we can if you take here cross products, you can rotate the finger I cross P. So finger first outward, then rotate toward the magnetic field. So taking the finger outwards, if you rotate, it will give me the thumb toward this side now. Okay. Give me force toward this side, but it will be perpendicular to current and field both. So it will be perpendicular to the dot here. Dot means perpendicular outward. So force will be in the plane. Plus it should be perpendicular to the magnetic fields. So it is force is parallel to the rail and perpendicular to the rod. So I'm getting a force parallel to the rail and perpendicular to the rod. If you still have a confusion regarding the directions, you can take it here as a 3D view. So current is coming here outward. So you can from I to B. If I rotate the finger from I to B, your force is coming on the right side. This way you're getting here the force directions. Clear? So if we see is perpendicular to the rod, I just try to slide it. Friction I'm getting in the opposite directions. Friction come in the opposite directions. So friction is balance the magnetic force as long as it is less than mu n. So you can say here magnetic force is BIL sine 90 degree. Why 90 degree? Current and magnetic fields are perpendiculars. So from the top view also you can see current and magnetic field perpendicular. From the side view also you can see current and magnetic fields are perpendiculars. So it is 90 degree. That should be less than our mu n. I hope was it okay? Clear? Yes, Vamsi.
Sir, one doubt, sir. The current in two rails are opposite, sir. Current passing in two rails, two metal rails.
Current in here we
Because
are
there is a circuit.
In this question you are saying or something else you are saying? So current in the wires is opposite, no doubt. We are talking about the effect on the rod. It is the rod which try to move. Okay. This circuit, the remaining circuit is not movable. Only this rod is experience. It's movable, and this is only going to move. Now, what is your once again? Say again. What is your point?
I'm telling that there will be two forces now, sir. One force is by one metal rail, another one is by another metal rail. And those two forces will be opposite due to current directions opposite.
which force is exerted by the rail? Rail is only exerting your friction and normal. Rail is not exerting magnetic force. Magnetic force is experienced by this rod. We are making the free body diagram of the rod. Okay? We are not making the free body diagram of the rails.
But
Okay.
the current is passing through metal rails, no, sir, not rod.
That is your doubt. Okay. Okay, say yes. Yes. See here, beta. Circuit, this is raw rails are theirs, and these rails are connected by this battery. And here is a wire or the rod. So this circuit is completed by this rod. The current flow this way. Okay. The current is going to be passing through this rod also. And this rod is movable. Rails are fixed. They are not movable. Understand? So we are making the diagram for this rod only. So there is an effect on the rail also, no doubt. There is an effect on the rail also. But question is about our rod only. We are talking here about the rod. Okay? Minimum mu required for sliding on the rail. Wire to slide. Okay? So this wire is trying to be slide. So on the rail, we are not analyzing. On the rod only, we are analyzing. Got it? So it's same as the last question. This one is there, similar to the last question here. It's same questions. But in this case, your rails are tilted. Slightly they have tilted. So inclined effect is also coming into these pictures. So if you understand the diagrams, you can solve that problems quite easily. Problems are not tough. Only directions are tricky. That's it. Directions are slightly tricky. So try to understand here this diagram. Once again, say AB and CDs are the smooth parallel rails separated by a distance of L and inclined to the horizontals at an angle of theta. So in the last problems, your rails are on the ground. Now rails are inclined. Okay, it's going to make it here as an inclined. If I take here, just a minute. So imagine here we have a inclined surface. This is our inclined surface, correct? That's your incline. You can consider a kind of table or etc. Okay? So table surface. If you tilt the table, that's going to make here as an inclined one. So here this is the inclined surface. Now on the incline, he put two rails. Two rails. Two rails are going to be kept on this incline. So we have two rails are going to be kept on the inclines. Are they? This is my rail number 1. Okay. So one more rail we can put it here as parallels. So two rails are given here as a parallel. Now in this two rails, next what is given here is a conductor EF is carrying a current I. And where is the conductor? Conductor is going to be touched this way. So we have this is a conductors which is going to be wire you can consider here. So wire is going to be placed on it. I hope you can understand the diagram now. So in this questions, this is my a kind of inclined surface. Some angle is there here, inclined angle is there, theta. And on this inclined surface, you have put a two parallel rails are there. So these rails are basically your metallic rails. And you can pass the current through them. And how you are going to be connect them with the batteries. Somehow, let's say battery is going to be connected here. And current is passing through them. So this current is coming and here is a conductors. So current is going to be make a closed loop in this way. Now these are fixed, but this rod is placed on it and this rod can slip in the downward directions. This is our pictures. So I hope you can see the picture here clearly, right? Before question once again. Actually, you can discuss the before question. This question is also similar to the last questions. Yes, Satish.
Sorry, yesterday you said that you will explain case 3, sir, once again.
So case 3 बताया था morning में. I explained the morning में case 3.
I attended class at 11:15, sir.
The classes attend at 11:15.
Yes, sir.
Actually, okay, then